Hi, welcome to the Mathemagic channel. So today we're going to be reacting to animation v geometry, and I have to say I'm really pumped and excited about this one. I'm really happy to be doing this video with you guys, and I wanted to first give you a big shout out and say a big thank you for all the absolutely amazing positive comments that you guys left on my animation v math video. So if you haven't watched it yet, please go ahead and watch it. It's a good video, and you guys have been so incredibly supportive. I've really appreciated it, and yeah, I just wanted to say that first. And so today we're reacting to animation v geometry by popular demand. You guys just asked for it. So I'm going to be doing my best to do it justice. I look at Alan Becker's videos like something which is a little bit like a super cool puzzle where you have to unlock all the hidden meanings inside of it. So without further ado, let's jump right in and enjoy the video. Thank you. Okay, I guess we're good to go. Let's see it. I'm excited. I hope you guys are too. This is just an advert though. Maybe I need to get one of those. Pretty cool. This might seem like nothing, but from the second coming or Stickman or Orange or whatever you want to call him appearing, we've gone from 0 dimensions, which is a dot, to 1 dimensions or 1 dimension, which is just a straight line, to 2-dimensional objects. So this is pretty cool. This is either going to be a vector or array. And if you're doing high school geometry, these are vertically opposite angles. So when you have 2 secant lines like this, you get vertical angles and they're equal. So nice representation of that. How he's thinking about it. He's like, what do I do with my angles? Like, imagine he was like an old Greek man trying to discover mathematics. This is pretty cool. And then here you have angles on a straight line, which are 180 and which give you 2 90-degree angles on the other side. Introduction of ratios. So if you have a ratio of 1 to 1, it means that really you have 2 sections. 1 plus 1 is equal to 2. And in school, like a lot of kids struggle with this. So make sure that if you're doing maths at school, if this is you and you're doing ratios, add them together, and then you have 1/2 and 1/2. You can change it into a fraction. So 1 out of 2 parts and 1 out of 2 parts. Introduction of ratios is good here. So the introduction of the letter phi, the golden ratio of 1.618. Super, super cool. Let's talk about it. So what is the number phi? So phi is 1.618, and it's a solution to this quadratic equation, which is x squared minus x minus 1 equals 0, which you can solve with the quadratic formula. It's equal to 1.61803398875. What's really interesting about it is if you're to do 1 over phi, so the reciprocal of phi, you actually get the same string of decimals, which is shocking for irrational numbers. It doesn't happen very often. And it's named by Mark Barr in 1914 after a Greek sculptor called Phidias. Yeah, and we use it to denote the golden section or the divine mean. So the way that you can think about it, and this is the Fibonacci rectangles for you, is that if you have a sequence which goes 1, 1, 2, 3, and the way that you construct that sequence is you do 1 plus 1 to get 2, 2 plus 1 to get 3, 3 plus 2 to get 5, 5 plus 3 to get 8, 8 plus 5 to get 13, 13 plus 8 to get 21. It's the Fibonacci sequence. What's really cool about this sequence is that as you go to bigger and bigger numbers and you divide one number by the previous one, you get very close to the golden ratio. So if you do 2 divided by 1, you get 2. If you do 3 divided by 2, you get 1.5. If you do 5 divided by 3, you get 1.6 recurring. If you get 8 divided by 5, you get 1.6. And you go all the way through to 21 divided by 13, which is about 1.65, and you can check that out. And so you get closer and closer to 1.618. Yeah, so this is a Fibonacci sequence, and it's supposed to make things very pleasing to the eye, and so we've used it in music. We see that pattern in famous paintings a lot, even in like modern AI paintings. Look at this one, beautiful spiral. And so yeah, you'll see this Fibonacci spiral everywhere, pretty much. And here's a representation even of the Taj Mahal with, again, that beautiful Fibonacci spiral. And so phi is the solution, or one of the solutions, to x squared minus x minus 1 equals 0. You can use the quadratic formula to solve it, and you'll get 1 plus root 5 over 2 and 1 minus root 5 over 2. 1 plus root 5 over 2 is phi. 1 minus root 5 over 2 is psi, which is another Greek letter. Root 5 is 2.236, and if you're to add 1 to this, you get 3.236, and if you divide that by 2, you get your 1.618, which is phi. And let's go back to the video. Notice root 3, which is 1.732, just a little bit bigger than 1.618. Help! Oh, that was sweet. He helped him out. Notice the 30, 60, 90 triangle. That's one of the special triangles, and it has side lengths 2, root 3, and 1. Very nice to see it showcased here. That is a 90-degree rotation clockwise. That's a geometrical transformation, so it's good to see that showcased as well. That is a reflection about the x-axis, so nice to see that happen as well. And a 150-degree rotation. It's nice to see all the angles on the inside, like as we go through, you know, all the different polygons here, and you've got like your pentagon, octagon, heptagon, and so on. How far are we going? Do you guys want to count how much that is? I'm going to say maybe it's 100 sides, which would be like a hectagon. Maybe I'm off. Maybe this is a lot less than 100. You guys can count. But if it was 100, it would be a hectagon, like in a hectogram. And if it was 1,000, no, actually 10,000, it would be a myriagon, which I really like that word. So because myriad means a lot of something, right? But you wouldn't, to the naked eye, it would just look like a circle. And we have a circle. So this is golden, not because it's a golden triangle, I don't think. At the bottom, notice you have pi phi, which would suggest the perimeter of the shape is pi phi. So that means the diameter, so the length across is actually phi. So the length across would be 1.618. And then the whole perimeter would be pi times phi. This is also showcasing the one of Euclid's theorems, which is if you stick a triangle inside of a semicircle, it's right angled. So it's nice to see that triangle in a semicircle shown here. I suppose this is a golden square because the side lengths are phi. He's so happy he can swim in it. This is one of the 370 proofs of Pythagoras' theorem. Beautiful to see it showcased here. He says, go fetch that square. This is another proof to Pythagoras' theorem. Very good. Did you see that? This is pretty cool. So phi to the power 0, which is 1, plus phi is equal to phi squared. So what's that all about? So you can actually take the quadratic formula solution for phi, 1 plus root 5 over 2, and if you had to add 1 to it, so if you add 2 over 2 to this, you get 3 plus root 5 over 2. And if you calculate phi squared, you also see that this is 3 plus root 5 over 2. So phi squared is indeed equal to phi plus 1. So you can do this numerically, and you can do this using Pythagoras' theorem as well. So pretty cool to see that being showcased here. They're friends now! Whoa, what's that? Whatever it is, looks pretty angry. Okay, I feel like we need to talk about this. Now that is a seriously angry 4D object. So why am I thinking that it's a 4-dimensional object? Well, first of all, when you look at a 3-dimensional object and you rotate it like this cube, it stays fixed in space almost. You can see that there's no like bits of it like folding onto itself or whatever. So this looks a lot like a 4-dimensional object because there's this internal type of movement. And also in the video, we started in 0th dimension and then 1st dimension, 2nd dimension, 3 dimensions. So it's normal that we're just increasing in dimensions. I don't know how far we're going to go if we're talking about string theory and 11-dimensional spaces and so on and manifolds. So we could go really far with this, and let's see later what happens in the video. In terms of 4-dimensional objects, you can see here a tesseract, which is a 4D cube. And here you can see that it's like almost like you have a light that's pointing at the object and projecting it in the back, and then from different angles, and it's kind of folding onto itself. And this kind of movement can only happen with 4-dimensional objects or higher. So that's why inferring that the shape in the video is a 4-dimensional object is probably quite accurate. A bigger shape would be a 24-cell polytope. So this could be definitely something that's very close to what we're looking at. But even this seems to be a little bit too organized, although it could be a good villain for the video. It seems to be a little bit too organized for what we're looking at, which looks really chaotic. Actually, it might be just like a random shape that doesn't have, you know, like a structure inside. So I was thinking maybe it's the Metatron Cube, who's just really angry. And the Metatron Cube is a divine shape in sacred geometry, where you have, you know, all the Platonic shapes contained inside of it. So in Metatron's cube, you will have the tetrahedron, the octahedron, the dodecahedron, and so on. So these all contained within this shape. And there is kind of, not a biblical, but a, I think it's in the Talmud, a Kabbalistic reference to this, where Metatron was an archangel, and it's not very clear whether he's a force of good or a force of evil. You guys can look it up. Please don't cancel me in the comments below. So please don't go blitzing my comment because of this. But, you know, maybe this is what it is. So do you think that it's a polytope? Do you think it's Metatron's cube? I don't know. So I think both of these are wild guesses, which could both be a little bit accurate. But, you know, I'd like to put this forward to you. It is a beautiful shape. And by the way, it sounds a lot like Megatron, who's the head of the Decepticons in Transformers. So he's a bad guy, and so the cube's a bad guy. I don't know. You can go ahead and tell me what you think in the comments below. Now, also, I wanted to point your attention to the Sierpinski carpet that's being left behind. It's very cool, like the way that this shape is constructed. Like you see some iterations here where you have, you know, a square, and then you make a hole in the middle, and then you take the other squares and you make holes in the middle of those, and then you keep doing that all the way to infinity. So you see up to C4 here, but you can do it up to C, you know, trillions or millions. And then the cool thing about this is it's like in a fractal zoom, where you can just keep zooming in on the shape and it just repeats onto itself to infinity. So without trying to break your brain, here's a fractal zoom of a Sierpinski carpet. And you can see how incredible this is. Anyway, I think it's great to see those references in the video, and I'm very glad that these were included. Let's get back to the animation. Run, Stickman! Oh, very cool. This is the fractional representation, recurring fractions representation of phi. His shots are getting deflected at some funny angles. I don't know if that means anything. That's our spiral from earlier. Is this like a hoverboard? Or did you say that's like a unicycle? More like a unicycle, right? Because it's in the middle. All right, back up a little bit here. Okay, so this shape, this is not a random shape. So, actually these tiles are not random at all. And if you saw the angles, it was 72, 72, 72, 144. We call this the kite. And then you have the dot, which you see on the right. and that's 36, 216, 36, 72. And so he's using, I'm not sure if he was using actually the kite or the dot as a paraglider. I have to check the video again. But this was something that Roger Penrose came up with. And those are two tiles that you can, so if you have to set them in a specific order, but given that specific tiling, so there's only one way that you're allowed to tile them, they will make what we call an aperiodic pattern, so a pattern that doesn't repeat itself, and that's very unique. So it's pretty incredible that that's showcased here, and this is something that came up in the 70s. So here's a Penrose tiling, and as you can see, there's like these star shapes, and there's other shapes that we call kings and things, named after a deck of cards actually. You can look these up, these are pretty cool. But you can see that like the placement of the stars doesn't really like repeat itself. It's just kind of random and all over the place. So yeah, this is a nice reference in the video, I think, to Penrose tilings. Now, one more thing that I'd like to share with you about Penrose tilings, and this will blow your mind, is that if you take, and this is not a joke, you can look it up, the limit as n tends to infinity of the number of kites divided by the number of dots, so the number of kite shapes divided by the number of dot shapes, you get phi. True story. So that's kind of incredible to see that mentioned in a video, and I'm wondering if it's a little wink to the fact that phi is actually not only inside of the shapes, but also in the number of shapes divided by each other, which is absolutely incredible, right? He's shooting octahedrons! This is insane! This is like a divine, sacred pentagon with a pentagram on the inside, lots of golden ratios rallying up. It's nice to see like the fractal on the side of the pentagon there. Look at these circles. There's like tangents to the circle and inscribed triangles. Actually, no, like just a piece of the triangle is inscribed. Very, very cool. Dumping golden rectangles on him. He doesn't like it though. Like the golden stuff seems to hit him a little bit. Okay, so if you trap him in a cube, you can make him go away. This really reminds me, you guys, and I apologize for the super old film reference, but of when in Superman 1, when we trap General Zod and send him into space. Yeah, maybe that's what this is referring to. He's pissed. He's really angry. So trapping him in a pyramid here, which is a tetrahedron. Trap him in a cube. icosahedron. So we threw the dodecahedron at him, and now you have these beautiful dragon curves. Amazing. Very, very cool. So these are the platonic solids that we just threw at him. I think this is extremely intentional. So if you look at the different platonic solids, you have your, triangular base pyramid, which is a tetrahedron. Then you have your octahedron, hexahedron, which is a cube, icosahedron, which is the 20-sided, and then dodecahedron, which is 12-sided. And so it looks like we threw fire at the villain, right? And it didn't work. And then we trapped him with air, and it didn't work. And then we trapped him with earth, and it didn't work. And then we trapped him with water, and it didn't work. And by the way, Plato, the way he looked at platonic solids is that, one turns into the other. So like air will turn into water, and then water will turn into earth, and then earth and air will turn into fire, and then they'll all like turn into each other. However, ether means the universe. And so when he throws the universe, then suddenly that works, because the universe is just like the most powerful thing. And so he threw the universe at this sort of chaotic shape, or this Metatron, or whatever it is. I still don't know what it is. And that worked. So yeah, the dodecahedron seems to be the most powerful shape. And it's the golden dodecahedron as well. And he took like the power, he harvested the power of more like golden ratios before he threw it. Very, very cool. Oh my God, absolutely amazing. This was in fact so cool, I'd love to watch it again. Absolutely incredible. So he steps into the dodecahedron, and these shapes now, they don't look 3D or 4D anymore. They look like maybe they're extra. Like, look at that blue shape here. Like, was that, I forgot which one it was. Was that the icosahedron, the blue one? It looks like there's a lot more stuff happening inside. So maybe it's a higher dimensional object. So instead of like 3 or 4 dimensions, I'll put an example here of like a 9-dimensional object, just for you to get a reference as to all these different interlocking points here. Also, if he's in the multiverse, and if this is like a wink at string theory, then are these like different versions of himself in like different universes? And then everything, all the elements are going towards some central light. Like, is that the center of the universe? What's going on with that? Oh, if you've got any ideas, please let me know in the comments below. Okay, so this is like a reference to animation v physics. Is this like, imagine that he's a mathematician, he studies geometry, but in an alternate universe, he would have been a physicist. if you met your alter ego from an alternate universe, a little bit like in Interstellar, when he goes into that library, you'd probably fall off your chair, like he just fell off the Dodecahedron. The end. And of course, I don't want this to end. Oh my God. But there's a couple of things to say about this. Okay, so here's my take on the ending here. There was an article published in 2003 inside of Physics World, which I've just pulled up here, which suggested that the universe might be a dodecahedron. And this is coming off measurements of the WMAP, which stands for the Wilkinson probe, which was sent into space. And by the way, all the measurements for the Wilkinson probe have now been recorded and all the studies have been completed. So until we have further kind of studies, this is where we're at in terms of humanity. And so we're looking to find the topology of the universe, and we managed to establish a certain number of things like the amount of dark matter or the number of atoms and things like that. And so in terms of the shape, it suggested that if it was a dodecahedron, it would agree with the formations of the cosmic microwave background, what we call CMB radiation. And so you can read this article and go and figure it out for yourselves maybe, but I think this is a wink to that. Yeah, so very, very smart in the video, I think. And if you're not convinced, this is what a Poincaré dodecahedral space with multiple Earths might look like. And if you watch the end of the video again, don't you think this looks really similar? So I think that this is definitely what Alan Becker's team is hinting at. Yeah, I'll play the end of the video again for you. Maybe you can think about it. So let's take another look at this now. So thanks for being with me and following me on this adventure through this whole video. But I just want to leave you with one closing thought here, because I think it's a cool one. Do you think the point of the video is to say that Plato, 400 years before Christ, correctly predicted the shape of the universe as a dodecahedron, which he called ether, saying it's the universe? Wouldn't that be incredible? Imagine if he's right. Like, how powerful would that be? And to finish, I just want to say, isn't math just beautiful? Don't you guys think? Anyway, please make sure to support our channel, and I shall see you on the next one. Bye-bye. Thank you.